Hi everyone, now we are at unit number 2 eigenvalues and eigenvectors, lecture number 5. So in the last lecture, lecture number 4, we established some relationship between characteristic polynomial and coefficients of characteristic polynomial and eigenvalues. Let me quickly recall it. So the characteristic polynomial a minus lambda I equals to, so the general form of characteristic polynomial is a naught lambda power n, because if a is n by n matrix, plus a1 lambda power n minus 1 plus up to so on, plus last one is a n. So assume this is 1. So from here, if lambda is 0, because I want what is determinant of a, if lambda is 0, then this implies determinant of a, substitute lambda is 0 here, 0 into I is 0, and determinant of a is equal to, here also substitute lambda is 0, then last a n will remains, the ln constant. Assume this is number 2. And after calculations, we got this form. The characteristic polynomial is of the form. We got this one as some a naught, or simply minus 1 whole to the power of n into lambda to the power of n plus minus 1 whole to the power of n minus 1 into lambda to the power of n minus 1, and its coefficient is a11 plus a22 plus a33 plus up to so on, plus a n, okay, and plus up to so on. This kind of coefficients we got, and assume this is number 3. Okay, it is number 3. So now let us compare 1 and 2. After comparing 1 and 2, and here, so compare 1 and 2, 1 and 3, sorry, 1 and 3. So after comparison, what we got here, so clearly instead of a naught, you are having minus 1 whole to the power of n. Compare equation number 1 and 3. So here lambda for n coefficient minus 1 to the power of n, here lambda n power coefficient is a naught, that's why a naught is equal to minus 1 whole to the power of n. And similarly a1 is a1 coefficient. A1, what is a1 value? So lambda power n minus 1 coefficient is here minus 1 whole to the power of n minus 1 into a11 plus a22 plus a33 plus up to so on ann. Okay, so comma up to so on. So these are the comparison of coefficients from equation number 1 and 3. So after this, now let us come to the relations. So first one, sum of the eigenvalues, okay, sum of the eigenvalues is equal to sum of the roots, indirectly sum of the roots. Here, since it is nth degree polynomial, n roots exist for this in the equation, polynomial equation. So that n roots are assume lambda 1, lambda 2 up to so on lambda n. Then sum of the roots becomes lambda 1 plus lambda 2 plus up to so on plus lambda n. So these are the sum of the roots, indirectly sum of the eigenvalues, right? And this one is nothing but minus a1 by a naught. Just to recall the theory of equations concept. Okay, so if f of x or some polynomial equation a naught x cube plus a1 x square plus a1 a2 x, okay, plus some b2 a3 is equal to some 0. And in this cubic equation, sum of the roots, if since it is cubic equation, 3 roots exist, then what is alpha plus beta plus gamma? That means if alpha, beta, gamma are the roots for this cubic equation, then sum of the roots is nothing but minus a1 by a naught, right? That's what I'm doing actually. Similarly, 2 roots product alpha into beta plus alpha into gamma plus beta into gamma. This I don't want. This I don't want. Only sum of the roots and product of the roots I want. So this one I'm erasing. It's not required. So I want product of the roots. Next one. Next relation. Product of the roots. What is the product of the roots? Alpha, beta, gamma. These are product of the roots. Okay. What is the sum of the 2 roots? Product of 2 roots. Then a2 by a naught like this. Plus a2 by a naught. So minus a1 by a naught plus a2 by a naught, and again minus a3 by a naught like this. So same relation I am doing here, same kind of relation. So minus a1 by a naught. So here what is minus a1? So minus a1 is nothing but, so minus as it is. So let me write here. So it is equal to minus a1 means minus 1 whole to the power of n divided by a naught. What is a naught? a1 minus 1 whole to the power of n minus 1. So minus 1 a1 value this much, right? Minus 1 whole to the power of n minus 1 into a11 plus a22 plus up to so on plus ann. Okay, whole divided by, so now a1 value is substituted. Next a naught value is from here minus 1 whole to the power of n. So minus 1 whole to the power of n. Now look at here, minus 1, nothing is there, here minus 1 it is actually. So minus 1 whole to the power of 1 I can write, and minus 1 whole to the power of n minus 1. It will become minus 1 whole to the power of n. Now that minus 1 whole to the power of n, this minus 1 whole to the power of n cancel out. Indirectly this is trace of a. Okay, trace of a. Trace of the given matrix A. Okay. Now matrix A, what is the matrix A? It is n rows and n column matrix. A11 is the first entry, A12 is the second entry in the first row, A13, A14 like that up to so on A1n. Similarly, second row A21, A22, A23 up to so on A2n. Third row A31, A32, A33 up to so on A3n like that. So that is n by n matrix. Okay, for that is A. So trace of A indirectly. So this is sum of eigenvalues. And similarly, the second one is product of the eigenvalues. Product of the eigenvalues. So product of the eigenvalues is nothing but product of the roots. Product of the roots. So here inter-degree polynomial, assume there are n roots, lambda 1 into lambda 2 into lambda 3 into up to so on into lambda n. It's a product. Again, product means the last one, right? So it's like this one. Look at minus a3 by a naught kind of. So last coefficient minus last coefficient will be this one. But here plus minus plus minus plus minus alternately sign changing. So here what should be the sign? The sign is, since it is integral polynomial, so the last one we cannot tell either it is whether it is plus or minus. So then in general we can write minus 1 whole to the power of n, the sign. If it is the first relation, then write minus 1 whole to the power of n is equal to 1, so that we will get minus. If it is second relation, substitute n is equal to 2, so that we will get plus a2 by a naught like that. So this nth relation, last relation, so minus 1 whole to the power of n and a n divided by a naught, and this is nothing but minus 1 whole to the power of n. Now what is a n? Look at equation number 2. From 2 a n is nothing but determinant of a. This is equation number 2 divided by what is a naught? A naught value is minus 1 whole to the power of n. To get the comparison of coefficients. So these two cancel out. Finally I got determinant of a. So data is nothing but product of the eigenvalue. This is what we have done in the last class. Just to recall it. So based on this, let's have some properties of eigenvalues of a square matrix. To get the properties of eigenvalues, the first one, property number 1, the sum of the eigenvalues of a square matrix A is nothing but what? Sum of the diagonal elements, or simply trace of A. Just now I proved. Okay, this is property number 1. So without calculating eigenvalues, I can tell what is the sum of the eigenvalues here. I am not telling individual eigenvalues. What is lambda 1? What is lambda 2? What is lambda 3? I am not telling that. Just I am telling what is lambda 1 plus lambda 2 plus lambda 3. That's it. Only sum I am giving you. Okay, by this property only sum I can tell. How to get sum? Simply take that matrix A and look at the diagonal entries. Simply add those diagonal entries and that will trace that sum of the diagonal entries is nothing but the sum of the eigenvalues. Next, property number 2. This also just now I proved. The product of the eigenvalues of the square matrix A is nothing but determinant of A. Whatever square matrix A you take. So product of eigenvalues is nothing but trace A. Det A, determinant of A. So based on these two properties, let's have one problem. Find the sum and product of the eigenvalues of the following matrices without actually finding the eigenvalues. So in this lecture, let's take this is number 1. That is problem number 1. Let's write it is problem number 1. Okay, problem number. Yeah. So without finding eigenvalues, we need to find out what is the product of eigenvalues and what is the sum of the eigenvalues. That is a problem. Okay. Now let us take first one. First matrix. Okay. First one. Assume this is matrix A. Okay. Matrix A is 6 minus 2, 2. Does it remind you anything, this problem? This matrix. Already I have done this. I have taken this matrix in the lecture number 2. Lecture number 2, first problem. This matrix only have taken lecture number 2. Lecture number 2. Problem number 1. Problem number 1. Look at once. Same problem I have taken. And we found their eigenvalues and eigenvectors. That is by calculations eigenvalues. Now here without calculating eigenvalues, we need to sum of the eigenvalues and product of the eigenvalues we have to calculate. So now I want sum of the eigenvalues. So sum of the eigenvalues. First, sum of the eigenvalues is nothing but lambda 1 plus lambda 2 plus lambda 3. If these three are eigenvalues, then their sum by the property. What is the sum? Simply trace of A. Trace of A. What is the trace of A now? Look at trace 6 plus 3 plus 3. How much total? 12. So simply sum of the eigenvalues is 12. How to cross verify this? Actually, what are the original eigenvalues for this matrix? Original eigenvalues. Have you remembered? Lambda 1 is equal to 2 I got there. And lambda 2 is equal to again 2 I got. And lambda 3 is equal to what I got? 8 I got. Check once. 2 to 8. Now what is the sum of eigenvalues? 2 plus 2, 4. 4 plus 8, 12. Look at 12 I got. Here we don't know what are eigenvalues actually. Exactly what are eigenvalues we don't know. Just we are telling what is the sum. But this is a cross verification. Already this problem I have done in lecture number 2, which is problem number 1. Look at there, I calculated eigenvalues which are 2 to 8. Now what is the sum? 12. Now it is cross verified like this. Okay. Next one I want product of the eigenvalues. So for the product of eigenvalues we want determinant of the matrix, right? So product of the eigenvalues. Next one, product of the eigenvalues. Product of the eigenvalues is nothing but what? Product of the eigenvalues. Simply lambda 1 into lambda 2 into lambda 3. Since only 3 eigenvalues exist because it is 3 by 3 matrix, is nothing but determinant of A by the property number 2. Since by using property number 2. Since property number, you have to mention that property also in exam. Since by using property number 1. Okay. And so what is the matrix first? So matrix A, so simply det A is equals to determinant of, what is the matrix? 6 minus 2 minus 2 3 minus 1, next 2 minus 1 3, 2 minus 1 3. Okay. What is the det now? So 6 into yes, 3 3 is a 9 plus 9 minus 1. Okay. Next minus plus 2 into yes minus 6 plus 2. Okay, and next one plus 2 into, hope you know how to find determinant, directly I'm calculating. So 2 minus 6. Okay, and this is nothing but 6 into 8, 48, and minus 4 minus 8, minus 4 to the 8, and minus 4, so again minus 8, isn't it? Yeah, now this is equivalent to how much? 40 and 32. 32 is a, so product of eigenvalue is 32. Let us cross verify product of eigenvalue is 32 or not. So actually what are the original values? The original values are 2, 2, 8. These are the eigenvalues. You multiply 8 to the 16, 16 to the 32. I am getting 32. This is cross verification. These are the original eigenvalues 2, 2, 8. Okay, no need to calculate what are the eigenvalues. Here only what are the sum of the eigenvalues, what are the product of the eigenvalues without computing them. Without computing what is lambda 1, lambda 2, lambda 3. Okay. Similarly, next, second one. Second problem. What is the second problem? It is the same lection number 2, problem number 3. 1, 1, 0. Have taken upper triangular matrix, right? 0, 2, 2 and 0, 3, 3. This upper triangular matrix I have taken. Lection number 2. This is lection number 2. Lection number 2. And problem number 2. Check one. Same problem I have taken. And yeah, now let us find sum of eigenvalues. Sum of eigenvalues. What are sum of eigenvalues? Lambda 1 plus lambda 2 plus lambda 3. Okay, there is nothing but what? Trace of A, right? Trace of A. Since by using the property number 1. Since by using property number 1. Property number 1. Okay. So now this is what is trace? Now look at 1, 2, 3. So 1 plus 2 plus 3. How much? How much is 6? So trace is 6. So actually what are the original eigenvalues? Let us cross verify. Have you remembered the eigenvalues? Simply diagonal entries are nothing but eigenvalues, right? For the upper triangular matrix. So 1, 2, 3. These are the eigenvalues for the upper triangular matrix. So do addition, you will get 6. Verified. Yes or no? Similarly, product of the eigenvalues. What are the product of the eigenvalues? Product of the eigenvalues is nothing but lambda 1 into lambda 2 into lambda 3. This is nothing but determinant of A since by using property number 2. Okay, property number 2 by using second property. And det A, determinant of A, let us find the determinant of this matrix. Okay, let us expand. So 1 into 3 to the 6 minus 3 to the 6, isn't it? 3 to 6, yeah. Next, minus 1 into 0. Okay, so this will be 1 minus 1 into 0 minus 0. Okay, and next last one minus 0 into again 0 minus 0. Okay, so I am getting zeros. I think something I have done wrong. Yes, this is 0, right? Remember this entry is 0 because I want upper triangular matrix, right? For upper triangular matrix, these 3 entries must be zeros, right? These 3 entries must be zeros for upper triangular matrix. Yeah, fine. That's what I'm getting here. Okay, let me do again this. So this become, so this will change, right? So 1 into 3 to the 6 minus 0, and all are the same. So this will be equivalent to how much? 6. So now look at original eigenvalues are these. Then multiply 3 to the 6, 6 1 to 6. I'm getting 6 verified. Similarly, you can take exercise problem number 3 and problem number 4 here. 3 and 4. Roughly, I will tell you. This one, same problem number 3 in exercise problem. Okay, this one exercise problems number 3. Okay, look at what are the eigenvalues there. I have given -1 and 1 are the eigenvalues I have given in the key. Check once. And what are the sum of the eigenvalues here? Zeros, right? Look at -1 plus 1 0. Now verify what is trace of this matrix. I minus I 0. Verified. Now determinant. What is the determinant? Minus I square is -1. So 1 minus 2. -1 you are getting. Determinant is -1. AD minus BC, right? Look at what is the determinant? What is the product of eigenvalues? -1. Verified simply. Oral calculation. Similarly, this one also it is same Excel problem, but problem number 2. I got eigenvalues 3, 0, 3 and 15. I think eigenvalues. Check once. Excel problem number 2. 0, 3, 15 are the eigenvalues. And you find what is the product of this eigenvalue? 0. So indirectly this det is equal to 0 you will get. Check once. And what is sum of eigenvalues? 18. Here what is trace of this matrix? 18. Verified like that. Okay. Take these two exercises and verify. Already I verified orally. Okay. Next one. So next, property number 3. The eigenvalues of A and its transpose are same. Eigenvalues A and A transpose are same. Let me prove it. So proof. Before entering into proof, you need to know two things. See, for example, let me write here. If B is any square matrix, B is any square matrix. Okay, B is any square matrix. And what can you say about determinant of B and determinant of B transpose? Find out both the determinants. What can you say about these two determinants? They are same actually. Determinant of B and determinant of B transpose are same. Take one square matrix roughly and verify this is true. Okay. How to prove this one? Again, in general, let us take 3 by 3 matrix. So let us take interest A11, A12, A13, A21, A22, A23 like that. You take the interest and find out what is the determinant of B. And next find out what is B transpose, and again find the determinant of that one. You compare both, they will be equal. So based on this idea, I'll give the proof for this. Okay, now let us start. So in this, first I want to calculate. There are two matrices I want to establish. So let lambda is an eigenvalue of A. So therefore A minus lambda I. Okay, this is matrix, right? Just matrix it is. A is a square matrix, lambda is a number, and I identity matrix. And if you simplify this again, one matrix you will get, right? Now I am finding its transpose. What is its transpose? Its transpose is A minus lambda I whole transpose. Okay, A minus lambda I. So this is a transpose of that matrix. Simply indirectly, like one matrix B have taken, its transpose is B transpose. Now I am comparing both the determinants, but both the determinants are same. So indirectly A minus lambda is nothing but my B here. So this is like B. It is like B, and it is like some B transpose. Okay, B transpose. I am doing transpose. Okay, this one. So now, so based on this one, both the determinants are same. So therefore here I can write. So determinant of A minus lambda I, okay, is equals to determinant of A minus lambda I whole transpose. Okay, nothing I have done, just one simple property I am applying. Determinant of the matrix and its transpose are same. That property I am applying here, nothing else. And one more, what is K1 times matrix A plus K2 times matrix B whole transpose? This property of matrices, by the property of matrices, this is equivalent to k1 into A whole transpose plus k2 into B whole transpose. Simply, and this is equivalent to k1 is a number, so k1 as it is, k1 as it is, and A transpose plus k2 as it is and B transpose. That's it. Simply numbers are as it is comes out, and a transpose can be applied to only matrices A transpose, B transpose. Similar same like I want to apply here. So now this is equivalent to determinant of inside. So assume this is like k1 into A, nothing is there means k1 is here 1. So 1 into A minus, instead of k2 you are having minus lambda, this is k2, okay. And instead of B you are having identity matrix. Now same property I am applying here, then it will get A transpose minus lambda as it is I transpose, okay. Now, so this will be determinant of A transpose minus lambda into identity matrix transpose, again identity matrix only, right? Take identity matrix, for example 2 by 2 identity matrix, you take 1 0 0 1, this is 2 by 2. What is transpose? Again same only, or you take 3 by 3 identity matrix, okay. Then what is transpose? Again same only, that's what I transpose is equal to I only. But what is this one? So I started with determinant of A minus lambda I, okay, and I ended with determinant of A transpose minus lambda I. So what can you say about this relation? Is it useful to us? Yeah, it is useful. Indirectly, what is this? This one is nothing but this is characteristic polynomial of A. Characteristic polynomial of A. And what is this? This one, this is nothing but characteristic polynomial of A transpose. Characteristic polynomial of A transpose. Now what can you say about now? So both the characteristic polynomials are same for which and which? Both A and A transpose. Here two matrices are, look at A transpose is one matrix, here matrix A is another matrix, okay. Both the matrix characteristic polynomials are same. Characteristic polynomials are same means their roots are same, okay. See, f of x is equal to g of x. F of x is one polynomial and this is equal to g of x polynomial. Indirectly, if both the polynomials are same, then their roots are also same. Yes or no? If 1, 2, 3 are the roots for f of x, then same 1, 2, 3 will be the roots for g of x because they are same, right? Same like this I am establishing here. So characteristic polynomial of A is equivalent to characteristic polynomial of A transpose. So therefore the conclusion is, so therefore what can I say? Roots of both the characteristic polynomials are same. Therefore, indirectly, roots are nothing but what? Eigenvalues. Therefore, eigenvalues of A and A transpose are same. Eigenvalues of A and A transpose are same. That's it. Okay. Next, property number 4. Property number 4. If lambda is an eigenvalue of a non-singular matrix, what is meant by non-singular matrix? Non-singular means determinant of that matrix should be non-zero. Non-singular means, okay. Non-singular means determinant of A is not equal to 0. That is called non-singular. Okay. If lambda is an eigenvalue of a non-singular matrix A, then 1 by lambda is an eigenvalue of A inverse. So lambda is an eigenvalue of A. This is given to us. Then what we have to prove? 1 by lambda means reciprocal of this old eigenvalue will be the eigenvalue of A inverse. That we need to prove. Okay. Let's complete proof. This proof is not difficult. Look at. So given that lambda is an eigenvalue of A, and what is given, A is non-singular, determinant of A is not equal to 0, non-singular, right? A is non-singular. So based on this information we have to prove that 1 by lambda is an eigenvalue of A inverse. 1 by lambda is an eigenvalue of A inverse. So this one we have to prove based on that information. Okay. So let us call this is 1. So from 1, lambda is an eigenvalue of A, therefore let x be an eigenvector with respect to the eigenvalue lambda. Okay, x be an eigenvector with respect to the eigenvalue lambda. Therefore, clearly we can write that Ax is equal to lambda x simply. Why? Because x is an eigenvector with respect to the eigenvalue lambda. So here what we can say is, look at here. Here lambda is an eigenvalue of A. Okay, and one more, x is an eigenvector of lambda. Okay, so this is called, so it means lambda is an eigenvalue of lambda is an eigenvalue of matrix A and x is an eigenvector of lambda. Okay, same phenomenon will apply here. Then what I am doing is, the next step, since determinant of A is not equal to 0, so since determinant of A is not equal to 0, therefore A inverse exists. Okay, since det is not equal to 0. So the next step what I will do is, assume this is number 2, from 2 implies multiply equation number 2 both sides with A inverse. Pre-multiply. Okay, let me write here pre-multiply. Pre means from the left hand side, post means right hand side, that means A into x into A inverse. So A inverse you are doing here, that's why that is post multiplication. Pre-multiplication means before, A inverse into A, like that. Okay, so now after that what will get? So A inverse into Ax, you are multiplying Ax to A inverse. Okay, and this is equivalent to A inverse into lambda x. Now from here, A inverse into A, these two together I will multiply into x is equals to, lambda is a number, then I will bring outside lambda, I am writing here, A inverse into x. Okay, I will write together like this. And A inverse into A will become identity matrix, and this is x is equal to lambda into, lambda into A inverse x. What is our main goal? Our main goal is, look at, I have to show that, we have to prove that 1 by lambda is an eigenvalue of A inverse. Means what? I have to prove this equation. 1 by lambda is an eigenvalue of A inverse means A inverse into x is equal to 1 by lambda into x. This one I need to prove, isn't it? How? Now I can say that this 1 by lambda is an eigenvalue of A inverse. Look at here, lambda is an eigenvalue of A in this equation. Similarly, if you are getting this equation, means what? 1 by lambda is an eigenvalue of, so this 1 by lambda, let me mark with a different, so this 1 by lambda is an eigenvalue of A inverse, like this. So indirectly we are expecting this equation. If you are proving this equation, then we are done. Have I got that? Look at here. Yeah, you send lambda to this side. So what will you get? What is identity matrix into x? x only, right, is equals to lambda into A inverse into x. Okay, and this is equivalent to, send 1 by lambda to this side, so 1 by lambda into x is equal to A inverse x. Okay, and rewrite the equation as like this: A inverse x is equal to 1 by lambda into x. Look at, I got the required equation. Look at, now I can say that this 1 by lambda is an eigenvalue of A inverse. So therefore conclusion is 1 by lambda is an eigenvalue of A inverse. That's it. Clear? Eigenvalue of A inverse. Of A inverse. So this is the conclusion. Now let's have one corollary. Same like that, if A is n by n matrix, then lambda 1 to lambda n are the eigenvalues of A. Then corresponding inverse eigenvalues are reciprocal of those eigenvalues. 1 by lambda 1, 1 by lambda 2, plus 1 by lambda n are the eigenvalues of A inverse. Okay. Next, property number 5. Property number 5. If lambda is an eigenvalue of A, then k into lambda is an eigenvalue of k into A, where k is a scalar. K belongs to complex number set here. Okay. K belongs to complex number set. Right? Right. K belongs to complex number set. Scalar. Okay. This means it is complex number. Right? Then again, same story. We start with the basic idea. Lambda is an eigenvalue of A. So then I will get it. So proof, try this with your own before I am doing. So given that, same story, given that lambda is an eigenvalue of A. Okay, let x be the eigenvector, with respect to lambda. So therefore clearly I can write that A into x is equal to lambda x. A into x is equal to lambda x. So now here what I want to prove that k into lambda is an eigenvalue of k into A indirectly. So we have to prove that. Simple one. We have to prove that k into lambda is an eigenvalue of k into the matrix A. This we have to prove. Okay, now start with this one. So let us start. One implies Ax is equal to lambda x. Now multiply both sides. With k number. K belongs to some complex number set. Take one number from complex number set, multiply both sides with this. Then what will you get? K into Ax, and here k into lambda x. Okay, k into lambda x. Right? Since k is a number, you can take multiply these two matrices and again multiply with k, or simply take k, you can take inside, no problem, because it is a number, it is not a matrix. Okay. See, remember one thing. Yes, I want to tell this. A into b need not be equals to b into A. Okay. If A and B are two matrices, A into B need not be equals to B into A. But if the matrices are like this, A into B into C, if it is given like this, what does it mean? First B into C how to do, after that we have to multiply with A. Or you can do first A into B, you can multiply, next to C. Multiply with C. This is okay. This is true. But this is not true. B is post multiplication, right, with A. And here B is pre-multiplication with A. So these two may not be equal always. Okay, it's need not be true. But if we are taking a number 2 into A is nothing but a into 2, whatever, doesn't matter. Matrix I have to multiply with 2 or matrix I have to multiply with 2, doesn't matter, both are same. In general you have to write, this is the right way of writing actually, correct way of writing. You can write like this also, but both the meanings are same. Okay, now k is like that. Okay, now this one I can write a into, let us take k inside, kx I can write. Just now I told you, just k is a number, okay, is equals to, again, k lambda into x. I am adjusting k, accordingly our requirements. You can write k, for example, look at here, k into lambda I can write, or lambda into kx also I can write, kx also, but that I don't want. What I want, I need to prove that k lambda is an eigenvalue of ka. That's why. Now look at here, look at this, k lambda is an eigenvalue of ka. So then bring ka this side, it's not required. Yeah, you can write like this also, but according to requirement I am writing. Okay, according to requirement I am writing. So therefore green, so k into a to x, you can write like this also. Look at, x should be alone, here x should be alone. Look at here, ax into lambda x, xx is alone, then I can say that lambda is an eigenvalue of a. Similarly xx alone, now I can say that this k lambda is an eigenvalue of ka. So therefore k lambda is an eigenvalue, k lambda is an eigenvalue of k into matrix A, where k is any scalar, k belongs to any complex number set. Understood? So from now onwards, if lambda is an eigenvalue of A, then multiply with some number with that eigenvalue, then that will be the eigenvalue of same multiplicity of the matrix A. Okay. Next one. Property number 6 is the last property, and I will do some problems based on this property in the next class. Okay. Last property number 6. If lambda is an eigenvalue of A, then lambda power k is an eigenvalue of A power k, where k is any positive integer. Okay. Look at it. It's also very simple. Proof. Yeah. Given that lambda is an eigenvalue of A, is an eigenvalue of A. Lambda is an eigenvalue of A. Let x be an eigenvector with respect to the eigenvalue lambda. So therefore clearly we can write that, therefore I can say that Ax is equal to lambda. It will satisfy this equation. Okay. So lambda is an eigenvalue of A and x is an eigenvector of lambda, like this. So lambda is an eigenvalue of A and x is an eigenvector of lambda, like this. This equation says like that. Okay. Lambda is an eigenvalue of matrix A and x is an eigenvector of the corresponding eigenvalue lambda. Now what we have to prove? We have to prove that lambda power k is an eigenvalue of A power k, where k is positive integer, k belongs to z plus. I'm writing z plus. Plus means positive integers. If k is negative, what happens? If k is negative, what happens? If k is negative, then you take k is equal to minus 2. If k is minus 2, what does it mean? Lambda power minus 2, okay. Lambda power minus 2 becomes 1 by lambda square. It is okay. But what about a power minus 2? It is meaningless. A power minus 1 is meaningful. That is inverse of a. Okay. Actually, a power minus 1, I could not say it is a power minus 1. This is not right way of pronunciation. A power minus 1 is wrong. A inverse actually it is. Okay. If I write a power like this, it is not meaningful. A power minus 2, a power minus 3. But a power 2 is meaningful, a power 3 is meaningful, up to so on. These are square of a. A square means what? A into a. A into a. Okay. But a power minus 2 is meaningless. That's why k is any positive integer. Next. So this we have to prove actually. Again you start with this equation number 1 implies. So 1 implies Ax is equal to lambda x. Okay. Multiply pre-multiplication I am doing. So if you are in matrix theory, compulsory pre-multiplication, post-multiplication compulsory required. You should be precise. Pre-multiply A. Pre-multiply the above equation with matrix A, the given matrix. Then what will get? A into pre-multiplication, A into Ax is equals to A into lambda x. Okay. But what is this? A square into x is equal to, now here, so lambda I am dragging out, will get Ax. Okay. But what is Ax now? Look at equation number 1. Ax value is lambda x. Substitute here. Ax is lambda x. Since by using 1, equation number 1 implies Ax value is lambda. Now this is equivalent to A square x, so which is lambda square x. So I started with A square x, now I ended with lambda square x. Again here what can you comment? Xx is same, so therefore here lambda square is eigenvalue of A square. So therefore lambda square is an eigenvalue of A square. So similarly, again take the same equation number 1. So I got this side. From here you continue. Again multiply with A both sides. Again what will get? A cube into x. Okay. And this side A into lambda square x. Lambda square you take out. You will get Ax. Again what is Ax? Again by equation number 1 it is lambda x. Again lambda cube x will get like this. See. We'll continue here. So if I multiply both sides again with A, so A square x. So this I am giving exercise, you complete this, and again this side A into lambda square x. Same this one I am taking here, and I am continuing. Okay. So from here again lambda square is out into Ax. Okay. So what is Ax again from equation number 1? Ax is lambda x. Now what you got? It is lambda cube x. Indirectly lambda cube an eigenvalue of A cube. So in this process I can say that therefore by continuous evolution of this, at the end we can get lambda power k is an eigenvalue of A power k. So this is a simple proof. Let's look at one corollary. So if lambda 1, lambda 2, lambda 3 plus 1, lambda n are eigenvalue of A is an n by n order matrix, then n eigenvalues are there. This is given to us. Then conclusion is lambda 1 power k, lambda 2 power k up to so on lambda n power k. These will be the eigenvalues of A power k for any positive integer k. Okay. And with this I will stop.